Hi everybody, thanks for joining. Today the topic is SBR Plus solver in HFSS, which is embedded in the Ansys Electronics Desktop platform. Our presenter today will be Stephen Anchong Liu. Stephen Liu has a BS degree from the one and only University of California at Santa Barbara, focused on signal processing and digital imaging processing. Most of the electromagnetics related webinars that you'll find on our website are completed by Stephen, and I will turn the controls over to him. So thanks everyone for joining us.
So let me show what we'll see. We'll see how you set up a RCS simulation SBR Plus and how to control the simulation. How do you plot a visual ray trace in the ADT environment, and what kind of filters we can do with those rays, and possibly the linked excitation blockage feature introduced as well. So a quick overview of what is a SBR solver. First of all, the SBR stands for shooting and bouncing rays. It's a asymptotic solver. It extends the physical optics to multiple bounces by geometrical optics rays, and then Ansys has extended the traditional SBR definition to SBR Plus, which adds to two extra features. It adds diffraction physics to the general SBR. Those two are the physical theory of diffraction, which is PTV, and as well as the uniform theory of diffraction, that's the UTD. So the main purpose of this SBR solver is to calculate scattered fields by using shooting and bouncing rays. So how SBR works? First of all, it needs a source, and then we need a scattered geometry. Then we'll need a observation point. Then the source shoots a bunch of rays to the scattered geometry. As you can see, this helicopter. The green the green area represents the rays that's being shooted onto the scattered geometry, and then it will plot a surface current on the scattered plane. The color and the dots represented on the geometry is mainly the scattering points where the rays are being shooted onto. And at the edge of the geometry, there will be diffraction. That's where this will be corrections due to the edge currents applied. So the PDD correction will be applied in this scenario. The edge currents will also radiate. The edge diffraction ray is launched if it is enabled. So the currents will paint it due to the ETD rays. So the currents painted by the SBR rays corrected at the edge plus the painted by the UTD rays will be summed together and give a whole plot of the painted currents. Of course, the rays will be bounces around multiple times, so there will be multiple bounces on the geometry. The fields added coherently at the observation point at every bounces, so that gives a entire plot of the currents after multiple bounces of the SBR and the UTD rays. The accuracy of the SBR plus simulation is directly determined by the ray density. The lower the ray density, the larger the footprint is. The bigger the ray density, the smaller the footprint is. The footprints are, and the accuracy is decreased as the as the accuracy increases as the ray density increases. Uh, how do we control the SBR solution setup in the ADT? It's um, there are several things we can control for the solver. There's so as we mentioned before, there's ray density per wavelength. Um, there's also the maximum number of balances you can specify. um, Also, as we mentioned before, the PTD and the UTD simulation setup at default is none. You can also have PTD correction as well as PTD correction plus UTD rays. But it doesn't mean that SBR Plus doesn't need a meshing. We do need a meshing for this solver. So we start off with a flat set faces, and then on the curve side, we can see we will need to turn on this allow tolerant meshing for SBR Plus objects. Uh, as you can see, for the tolerant meshing on the top surface is finely meshed, where the not tolerant is uh, is very uh, very weak. The ray footprint uh, is correlated to the mesh triangle, as you see on the green triangle represents the mesh represents the ray footprint. So there's two ways to access SBR Plus solver in AEDT. Back in the R19.0, the SBR Plus region was introduced, so it could be a hybrid region in the driven model analysis. And then later in R19.1, SBR Plus solver was introduced. In that setup, all the regions will be SBR Plus region, and no ports will allowed, meaning as you can see, there's no port field display in the SBR Plus solver. Couple boundary conditions we can have in SBR Plus. So other words, in SBR Plus region can be assigned the following boundaries: finite connectivity, perfect E, perfect H, impedance or layered impedance boundary, and lastly, a newly added boundary condition, Fresnel boundary. Uh, Different kinds of excitations can be implemented in SBR Plus. We can implement a plane waves. We can also use a linked excitation that as from an outside source. For example, like we can use those like halfway dipole, parametric beam, parametric slot, and etc. We can also use parametric antennas. So let's take a look at an example we already have of the RCS. It's a trihedral corner reflector. It's metallic. It's a size of about 20. The size of it is about 20 lambda of the frequency of the wavelength. Uh, so we compute a monostatic RCS, and we will show you how the SBR Plus result compares to the full wave solver integral region, integral equation, IE solver, and the impact of different simulation settings. So we have a this trihedral RCS setup. Let's take a look at different setups we have here. So as you can see, this is SBR Plus solution setup. We we have a perfect reflection, a perfect E boundary condition. We're trying to calculate the RCS at the XY plane. So we give a incident wave excitation in, that's in the XY plane, and we'll see how different settings that gives you different results. We have a SBR plus SBR setting, as well as a SBR setting with UTD PTD. And one thing we need to pay attention to is that the default for compute far fields are usually turned off, so we do want to turn it on when we're doing the SBR analysis. So let's take a look at with or without the diffraction. So there are two similar plots. One is with the diffraction, one is without the diffraction. As you can see, there's not much big difference. The without diffraction results takes only 4 seconds to solve, while with the diffraction option, it takes about 5 more time, about 19 seconds to complete. But the compares, but the results doesn't have much big of a difference. But what if we take a look at the difference between these two the SBR solvers with the full width solvers? Now, it's still not much of a big difference, but the full width solver takes way much longer. As you can see, 36 minutes to complete, where the previous two is 4 seconds and 19 seconds. So these are just with the default settings. So now we take a look at we make a variable um, for so let's take a look at the compare the difference between the different ray density settings. So we set a max number of bounces at 5, with different ray density. Um, so ray density at 2 takes 1 second to complete. Ray density of 4 takes 4 seconds to complete, and ray density of 8 takes 16 seconds to complete. As you can see, not much of big difference neither. Then we can take a look at how many we can set the maximum number ray density at 4 fixed with different max bounces, the maximum bounces. So now we can, this is where it makes a difference. The maximum bounces for 1 bounce, 2 bounce, 3 bounce, and 5 bounce. So all of them takes uh, pretty quick, just a couple of seconds to complete, but the results is fairly different. So after that, I can show you how to plot the visual ray trace, which we already have. So we can do that by go to field overlays, plot VRT, and click on SBR, and we will just take everything as default. So now, initially, when we click on that, there will be an arrow saying the visual ray trace is too close to the CAD surface. So we want to change the observation point. So we go to the um, the visual ray trace SBR. We go to the plot that we just plotted. The first plot was was already plotted before the presentation. The plot 2 was the one that I just created. We can change the coordinate to change uh, the source. Let's set it at 50. Right. So it was aborted at the first, but now it's since we changed the source location, now it's all set to go. A couple of things we can play with. So we can change the ray density. Now it's at 2. We can change it to 8. Maximum number of bounces. Uh, well, first of all, let's try to understand what's in this plot. Uh, if we go to the top, uh, the go to the top menu of the ray tracing plot, it will tell you that what the color represents. So right now the color represents the number of reflections. The green means one reflection. Blue represents two reflections. Yellow is three. Um, red is four. And we can define the color by with different definition. Now it's number of reflections. We can change it to number of transmission. We can also define it as the bounce number. Um, we can so this jolt exit was turned on. We can turn it off. So if we turn this on, all we're seeing is the exit exit rays. We can also, if you don't want to see them as lines, we can draw them as points. So there will be showing you scattering points of those rays. We can also draw ray footprints. So those are something we can play with on the top menu, on the very on the plot itself. Um, we can change the ray density. That's per lambda. Um, we'll have the maximum frequency you can change with. What else can we change? Right, we can, and there's a filter. Uh, number of bounces. If we turn this off, this will be the entire source. If we give a criteria, initially it was at 0, and this is at 1. This will be all the incident rays. So if we don't want to see any incident waves, we can change this to 1, and now everything we see will be the rays exiting the reflector. We can also give a filter to the shoot filter. So we can define we already have two boxes defined. It's a non-model box for the inner box. We click on inner box and we go to the plot. We click on raise inbox. Box inner. This will be the rays that's shooting off from inside the box. And we'll also have a box outside of the reflector. You can choose box outer. This will be the rays shooting out of the box. So those are some of uh, the capabilities we can play with in the AEDT for SBR Plus solver. Thank you very much for joining today. Have a nice day.